Conjugate channel. Please do remember, subscribe, like, and share. Thank you. Today we are going to learn about ionic equilibria. We have a quick review about the definition. First, what is acid? What is base? There are three definitions for acid and base. The first one is Arrhenius. According to Arrhenius, acid is a substance that dissociates in aqueous solution to produce hydronium or hydrogen ion, which is H plus or H3O plus in aqueous solution. By referring this example, HCl, when it dissociates, it will form H plus ion. So this is acid. HCl is an acid. While for Arrhenius base, substance that dissociate in aqueous solution to produce hydroxide ion, OH negative. For example, sodium hydroxide dissociate from sodium plus and OH negative. So OH negative, this is Arrhenius base. But this one not general in use. Okay, the most common one is Bronsted-Lowry. What is Bronsted-Lowry acid? It's a substance that can donate a proton H plus to another substance, proton donor. So over here H plus we can refer as proton. So this acid donate its proton to H2O and then form H3O plus and itself becomes Cl negative. If you learn later, we are going to identify this is acid and its pair we call it as conjugate base. Okay, Bronsted-Lowry base is a substance that can accept a proton from another substance. So we can call it as proton acceptor as well. Ammonia accept a proton, become ammonium. So this is base, this is conjugate acid. Okay, it accept a proton from H2O. Okay, so this is acid, this one is conjugate base. Okay, yeah. So based on this Bronsted-Lowry, we can observe, okay, if the reactant is acid, well, it become the product, it will become conjugate base. And then acid, one of the reactant is acid, meaning that another one automatically is base. So this base will accept a proton and then become H3O plus. Okay, so this pair is base conjugate acid. Okay, meaning that from one equation we can identify Bronsted-Lowry acid and Bronsted-Lowry base from two reactants. Okay, the third definition is Lewis acid. Lewis acid is a substance, can be atom, ion, or molecule that can accept a pair of electrons to form coordinate covalent bond. If you notice, right, this one we learned in chapter 4. Okay, if we want to form the coordinate covalent bond for Lewis acid, okay, it must have a empty orbital. So for example, boron and aluminium is electron deficiency species. They form incomplete object. That's why it can accept a pair of electrons from Lewis base. What is Lewis base? It's the substance that can donate a pair of electrons to form a coordinate covalent bond. Meaning that Lewis base normally there are lone pair. So for example, ammonia, there is lone pair over here. Water, there are two lone pairs for the oxygen atom. Okay. Next, this is what I said just now about conjugate acid base pair. So the conjugate acid and conjugate base pair is according to Bronsted-Lowry. So for conjugate acid, a species form when a Bronsted-Lowry base accept proton. So we look at this example. Okay, this is acid. Okay, so it will donate proton. Once it donate proton, it become conjugate base. So this is the definition for conjugate base. A species form when a Bronsted-Lowry acid donate proton. So this is the Bronsted-Lowry acid donate a proton, then it form conjugate base. And then this is base. So conjugate acid is a species form when a base accept a proton and then become conjugate acid. Okay, this is another example. So this is acid. Acid will donate proton. Once it donate proton, it become conjugate base, CiO4 negative. Here you check. Initially, there is no charge. Once it's donate proton, okay, means the H plus, it will become negative ion. And this is base, okay, Bronsted-Lowry base. It will accept a proton. After it accept a proton H plus, it will become N2H5 positive charge. After acid-base definition and conjugate acid, conjugate base definition, now we look at strong acid, strong base. There are three important points you have to remember. The first one, for the strong acid and strong base, it dissociate completely, or we can say 100% ionized, high concentration, and one-way arrow. If we refer to strong acid, it dissociates completely in an aqueous solution to produce high concentration of hydronium ion, H3O+. If you check the equation, one-way arrow. So nitric acid dissociate or ionize in water, it forms H3O plus and NO3 negative. Okay, try to recap the definition of conjugate acid, conjugate base. So this one is acid. So it will pair with NO3 negative. NO3 negative is the conjugate base. Okay, this is acid. Automatically, its partner is base. So this base will accept a proton, become H3O plus. So this is the conjugate acid. Okay. For strong base, dissociate completely in an aqueous solution to produce high concentration of hydroxide ion, 100% ionized. So in this case, this is Arrhenius base because OH negative is produced. Next is weak acid and weak base. For weak acid and weak base, dissociate slightly, partially, has low concentration, and is a reversible reaction. So it can represent by reversible arrow for weak acid or weak base. So the keyword dissociate slightly in an aqueous solution to produce for acid, low concentration of hydronium ion, for base, low concentration of hydroxide. So these are the two examples. HCN, ionized in water, produce H3O plus but Cn negative. Okay, and then for weak base, ammonia, okay, ionized in water, form ammonium and hydroxide ion. So this is base, conjugate acid. This is acid, conjugate base. Okay, these are the few examples for strong acid and weak acid. I think you're all more easier to identify the strong and weak acid compared to conjugate acid or conjugate base. So HCl, nitric acid, hydrochloric acid, sulfuric acid, HBr, HI, all of these, right? Perchloric acid are strong acid. Okay, normally for the organic acid, for example, benzoic acid, ethanoic acid, okay, is weak acid. Other example included oxalic acid, sulfurous acid, and so on. Okay. For base, normally strong base with hydroxide ion. So all these example with hydroxide ion. And then weak base, there are few example: trimethyl ammonia, pyridine, ammonium hydroxide, water, and ammonia. Okay, please take note that even though ammonium there is hydroxide, but this is weak base. Okay, ammonia is the most common weak base. Next, about pH scale. pH can be acid, neutral, or basic. Depends the value. If less than 7, meaning that the concentration of hydronium or hydrogen ion is higher. So pH less than 7 is an acidic solution. If equal to 7 is a neutral solution, meaning that the concentration of H plus and hydroxide ion is the same. And then pH more than 7, meaning that the hydroxide ion is higher. So it is a basic solution. All the pH scale, right, can measure by various tools. Can be acid-base indicator like phenolphthalein, alizarin yellow, methyl orange, or methyl red, or pH paper, pH meter. Okay, now we look at what is pH and pOH. What is the relationship between pH, pOH with Kw and pKw? First, you have to know P actually is equal to negative log. When the concentration of hydroxide or hydronium ion is given, you can calculate the pH or pOH by press your calculator in negative log. The higher the concentration of hydronium ion, the lower the pH. Same for hydroxide ion. Higher, lower pOH. Okay, this is a new constant that you have to know, Kw, ion product constant for water, which have the value 1 times 10 to the power of negative 14 at 25 degrees Celsius. How do you get this value? This value is concentration of hydronium ion times hydroxide ion. So Kw equal to hydronium ion times hydroxide ion. So we can use this formula to find out the concentration of hydronium ion or hydroxide ion if one of the concentration is given, because Kw is a constant with 1 times 10 to the power of negative 14. If in pure water, meaning that the hydronium ion and the hydroxide ion is same, means 1 times 10 to the power of negative 7 molar, pH equal to 7. Okay, since we know this relationship Kw equal to hydronium ion times hydroxide, if we insert negative log for all these measurement, okay, we can get negative log times 1 times 10 to the power of negative 14 actually is equal to 14. Okay, and then just now we say negative log actually is P. So meaning that pH, okay, negative, negative, positive. So pH plus POH equal to pKw. So pKw with the value of 14. So we must know pH plus POH equal to 14. Need to know the formula of pH plus POH equal to 14. And this one, Kw equal to concentration of hydronium ion times hydroxide. So you must know how to convert for this. This is the last part of this video. It's about acid dissociation constant Ka and base dissociation constant Kb. Okay, this concept is exactly same as what you have learned in chapter 6, Kc and Kw. Based on the equation, and then use the concentration of product over the concentration of reactant, ignore solid and liquid. Okay, so over here, based on this equation, the product is concentration of H3O plus times concentration of A negative ion over concentration of HA. Water liquid is ignored. Okay, you have to know stronger acid, higher concentration of the H3O plus ion, hydroxonium ion or hydrogen ion, larger Ka value, and then lower pKa, because the value of Ka and pKa is inversely proportional. Okay, same for base dissociation constant Kb. Okay, write down the Kb and then okay, concentration of product pH plus times the concentration of hydroxide ion over concentration of B, the base. Stronger base, higher hydroxide ion, larger Kb value, low pKb value. Now, let's try one example related with Ka and Kb. Tutorial question 11. The table below shows the base ionization constant Kb for several selected compounds. Okay, so there are 4 compounds. First, arrange the compound in order of increasing strength of base. As we know, high concentration of hydroxide ion, larger Kb value. So in this case, in order of increasing means from the weakest one, from the smallest Kb value, arrange until the largest Kb value. So based on here, the smallest one is this one. So this is number 1. Okay, followed by 2, number 3. Okay, so this one is the highest one, meaning that this is the strongest base among these 4 species. Okay. B, give the structure of conjugate acid for each compound. And there are 2 questions. Arrange them in order of increasing strength of acid. Okay, so conjugate acid. According to Bronsted-Lowry Base, okay, it will accept a proton and then form conjugate acid. So after it accepts proton, it will become NH3 positive. This will become NH5 positive. And then this will become NH4 positive. And then this will become NH3OH positive. Okay, so these are the conjugate acid. Then arrange in order of increasing, okay, increasing order of strength of acid. So just now this is strongest base, meaning that now it is the weakest one. Okay, oh sorry, this one is a weakest base, this is the strongest one, so strongest, so this is number 4. Okay, so this is number 1. Okay, number 2, number 3, number 4. Okay, let's check your answer. Okay, yes. Okay, this is the way to arrange the compound according to the strength of base, increasing strength of base. So you must use this one, bigger than, bigger than, bigger than, and then use this arrow to represent increasing strength of base. Okay, so for B, question number 1, okay, this is the pair, base conjugate acid pair. This is the base, this is the conjugate acid. Okay, same for here, this is the base, this is the conjugate acid. And same for here, this is the conjugate acid. Okay, just now this one is the weakest base, now become strongest acid. Okay, this one is the strongest base, now become the weakest acid. That's all for this video. Please do remember, subscribe, like, and share. If you have any question, please don't hesitate to consult with your lecturers. Stay at home, stay safe. Bye.